this short video is on DFT, the computation of DFT. Basically, there are two approaches for the DFT computations. One method is called the expansion method, and from the fundamental principle, and the second method is the matrix method. So basically, the DFT is defined for a sequence x of n, given input sequence x of n. It is defined as sigma n is equal to 0 to n minus 1, the given function x of n multiplied by e to the power minus j 2 pi by n kn. Now there are two variables are available here. The variable n is basically ranging from 0 to n minus 1, and the value of k is also ranging from 0 to n minus 1. X of k is the DFT, the Fourier transform model, the sequence, whereas the x of n as the input, discrete time input. Now, just for the simplicity, we can substitute the value e to the power minus j 2 pi by n is equal to wn. Then the above equation can be simplified as x of k is equal to the sigma x of n multiplied by wn to the power kn, and this wn is called as the Tweedale factor. Okay, can be calculated by the equation wn is equal to e to the power minus j 2 pi by n. And as I have mentioned before, there are two approaches. One method is the expansion method from the fundamental principle, which is the fundamental law, and the second method is what the matrix method. It is very easy method compared to what you call the expansion method. Now let us assume an example here. X of n is equal to 1, 2, 3, 4, and this is a 4-point sequence, and we want to find out a 4-point DFT. So we have to change the limit now from 0 to 3, because we have totally 4 samples, so 0 to 3, x of n, wn, kn. Then we can substitute the running variable, which is n, from 0 to 3. So the first time we are substituting, because this is a summation series, so the first time we are substituting 0. Wherever n is there has to be replaced by 0. So we'll get x of 0 wn of 0, x of 1 wn of 1k, which is k, then x of 2 into what wn of 2k, then wn or x of 3 into wn of 3k. Now this is the basic sequence we are getting now. So if you want to calculate the values of the output value, the FFT values, you can substitute value one by one. For example, if you are interested in when k is equal to 0, you can substitute k is equal to 0. So when k is equal to 0, you have x of 0 wn of 0, then x of 1 wn of 0, x of 2 wn of 0, and x of 3 wn of 0, because wherever k is there we are substituting. So you can find that k is here, k is here, k is also here. When we substitute this value, k is equal to 0, that particular term become 1. So which means that we are having the coefficients, all the coefficients, input values, which are x0, x0, x1, x2, and x3. All the coefficients become 1. Therefore this is nothing but the first value is nothing but the sum of all the input numbers, which are 1 plus 2 plus 3 plus 4, which is 10. So the first value, which is correspond to x of 0, is equal to 10. The next case, we are substituting k is equal to 1. Now wherever k is there, we substitute 1. So this value is originally is 0, but here is 1k, so this has become 1. Here is 2k, so this has become 2. This was 3k, so this become 3. Now these parameters, w4 square, w4 to the power 3 can be directly obtained from the Tweedale the table, and by substituting these values, we can see that we have minus j here. Here is 1, here is minus j, here is minus 1 and j. We can get the answer minus 2 plus 2j. We have 1 minus 2j minus 3 plus 2j. If we simplify, we will get what? 1 minus 3 minus 2j plus 4j, and we got the answer minus 2 plus 2j. In the same manner, we can substitute x of 2. So wherever k is there, that k has to be replaced by 2. So this is originally is like what? 0. This was 2k. So nk. So which is nk. So 1k. So 1k become 2. 2k become 4. 4k become 3k become 6. Okay. So if you substitute the same value here, we will get the answer -2 in this case. In the same manner, we can calculate the x of 3. To find out the x of 3, we are substituting k is equal to 3. So 1k becomes 3, 2k becomes 6, and 1k becomes 3, 2k becomes 6, and 3k become 9, and this is already 0. If you substitute all this value here, then we will get the value of minus 2, minus 2j. So we have all the values: 10, minus 2 plus 2j, minus 2, minus 2, then minus 2, minus 2j. So this is the answer we got it by using this particular method. This is called the expansion method. Now the second method is called the matrix method. In this particular matrix method, the normal structure of the matrix is like what do you need? We need a the output matrix, which is the x of k. So this is basically for the DFT computation. So the input is x of n, which is the discrete time signal, and the output is the x of k. Then we need a coefficient matrix. So if the size of the input matrix is 1 by n, so normally this must be a column vector, one column and several rows. So one column and n rows, and if it is n, therefore the order of or the size of this matrix is but n by n. For example, if it is 1 by 4, for example, if n is equal to 4, then this must be like what, a 4 by 4 matrix. This must be what, 1 times 4, and this is also 1 times 4. This is the basic rule. So and the normal structure is like this. The first row, okay, for example, in the case of n is equal to 4 DFT, the first complete elements of the row is like what, 1, and same way the first column is also going to be 1. Okay, now look at the first row, the second row. It is with the power of 1, 2, and 3. Okay, the third row you can find 2, 4, 6, and the fourth row we can find 3, 6, 9. So the same way it can continue if the size of the matrix is in a larger matrix. So just remember the sequence. The first row and the first columns are exactly all ones. Second row, the first element is with the power 1, second element is power 2, third element is power 3, and the third row 2, 4, 6, and the fourth row 3, 6, 9. So same way you can go for higher sizes here. And this one is the input matrix. This is already given. Okay, now let us try to solve this question. You can also find we can find the value of the the W coefficients from the table sheets, and you can get a matrix like this. So suppose if we try to solve this question 1, 2, 3, 4, which already we have solved before. So the first array, the first row is completely 1, 1, 1. The first column also 1, 1, 1, and then you will get a pattern here: minus j, minus 1, j, minus 1, 1, minus 1, j, minus 1, minus j. So this is the pattern here. Or you can, if you have the drill sheet, you can get the values directly. Now we basically doing a matrix multiplication. So if you are going to do multiplication of an n by n matrix, if you are going to multiply with what you call 1 by n matrix, okay, then n by 1 matrix, then the answer is supposed to be like what, so if you multiply n by n coefficient matrix with the n by 1, the input matrix, the rows, the column of this is matching with the row of the second, and therefore matrix multiplication is possible, and the output dimension is what, n by 1. So which means that you're supposed to have n by 1 matrix. So I have to change this one. This matrix supposed not be 1 by n, it's supposed to be n by n matrix, n by 1, and this is also going to be n by 1, n rows and 1 column. Okay, simply speaking, it's a column matrix. This is a column matrix. This is a square matrix. Okay, and this is also a column matrix. So column matrix means what? Only one column, but there are several or n number of rows here. So please remember this rule. Here is column matrix, here is square matrix, and here is again a column matrix. So what you are going to get in the answer, n by 1 is a square matrix that is going to be multiplied by a column vector or column matrix, and this is going to give you a result of n by 1, n cross 1, and that is supposed to be the output matrix here. Okay, so this is the basic rule. and if you substitute these values, you can get the final answer by multiplying the element. So each row, take each row, for example, you take this particular row and you take this particular row and just fit this row in this manner. So you will get 1 1 1 and 1. So each factor you multiply, so then you just add, so that you will get this particular step here. Okay, the next time what happen, you have to fit the second line, which is this line. We are going to pick this line, and you have to pick the put in the same order. Okay, for example, 1 minus j minus 1 and j, and again you get this particular rule, and the third time you can get this value, fit in the same manner, you will get this part, and you will finally get this part, and it normally results like what, 10 minus 2 plus 2j minus 2 and minus 2j. This is the way how the matrix multiplication can be done. So take a row, you fit that row to the input matrix. Okay, flip it and then input multiply the coefficients, then you add. So there are multiplications involved, then finally you need also additionals involved. Now in this particular case we are going to discuss about the IDFT, which is inverse discrete Fourier transform. The only the difference, the main differences are the dimensions, everything is same. This is again, as we said, this is n by 1, this is n by n, and this is also what, n by 1. So there is a coefficient, or this is called as scaling coefficient is there. So in this example I use 1 by 4 because this is a 4 by 4, I mean 4 input case, or the 4-point DFT. So if it is a 4-point DFT, then divide by 1 by 4. If it is an n-point DFT, then supposed to be divided by 1 by n. Now there is also one other difference, as you can see that the rest of everything is same. So this is now the output, which is basically a discrete signal, and here is the input, which is basically the DFT. Okay, DFT values. Then these are the matrix actually. So the matrix also, there is no major differences. This, the first row and the first column, as we said in the previous slide, it is exactly the same. Now all these coefficients, the powers become minus. That's the only difference. So you can see that the coefficients are exactly same as the previous coefficients. There is no difference except that the powers are minus 1. So since the powers are minus 1, in the coefficient matrix, wherever j terms comes, you will find a sign change there. So if you compare to the previous example, wherever there is j, that sign will change. For example, in the previous case, this was minus 1. So in this case, this is going to be plus. Okay, and previously this was plus 1. So in this case, it is going to be what, minus 1. So the change happened to only the the j terms. Okay, then you do the same procedure. You take this particular row, like we have said explained before. So you take this particular row and fit in in this particular manner, 1 1 1 1, then 1 1. Then you just simplify. When you simplify it, you will end up with what called 4, and that 4 has to be divided by the scaling factor. Then you will get 1. Same way you can continue. So you will find 8 by 4, which is equal to 2, then 12 by 4, which is 3, and then 4. Okay, which is the x of 3. Okay, so this is the basic way of how to compute IDFT. Now, if the question is a DFT with 8 point, the difference comes, it must be an 8 by 1 output matrix, and we have an 8 by 8 square matrix, the coefficient matrix, or the tutorial matrix, and then we have an 8 by 1 what you call the input matrix. Okay, in same way, if it is an IDFT 8 point, this must be what, 8 by 1 output matrix of x of n, 1 by 8 is the scaling factor, 8 by 8 coefficient matrix, then 8 by 1 the input matrix. Okay, so this is the way how you calculate the DFT and IDFT of the discrete sequences. Okay, best wishes. Thank you.